All right, I want to talk tonight about predicting NMR spectra. We didn't have a lot of time in class today to do examples of this, and I think it's important that we go over an example focusing on the four key pieces of information: the number of peaks, peak position, multiplicity, and integration. And so I want to go through a couple of examples that I think will help you as you look to work on the problems that you're going to have for Friday. All right, so here's a molecule that I want to start with. Our first example. This molecule's name is ethyl acetate. And what I want to do is predict all of these things: number of peaks, peak position, integration, and multiplicity. So let's first fill in the protons. And then let's predict number of peaks. All right, so if we look at this, we have A, B, and C. All right, so number of peaks, we're going to predict 3 peaks. Right? Let's do peak position. And again, peak position, we're going to focus on protons that are close to electronegative elements. Those are going to be de-shielded to the left in the spectrum. Right, so peak position, and again we're thinking de-shielded to shielded, and again de-shielded, electron poor, shielded, electron rich. Right, and if we think about that for this molecule, it's pretty clear that the protons at B are closest to the electronegative element. So if we go from left to right in the spectrum, we're going to have B. Then we look at A, which is 1 bond away from a carbon attached to 2 oxygens, so A will be next. And then C will be last. All right, so we can predict the peak position. Now we need to look to integration. And again, remember, integration is just a measure of how many protons are giving rise to the peak that you're looking at. And again, if you remember from calculus, integration means area under the curve. So what the computer is doing is actually measuring the area under the peaks. And then it gives you a ratio of that area, which relates to the number of protons that gave rise to the peak. All right, so integration is just a ratio of area that corresponds to ratio of numbers of protons giving rise to each peak. So if we look at B, A, and C, 2 protons give rise to B, so that will be 2. A, we have 3 protons, so it's 2 to 3, and then C is also 3. So the integration ratio will be 2 to 3 to 3. Okay? And then finally, we have multiplicity. And multiplicity is probably the most confusing of the things that we learn from proton NMR. And again, the thing to remember about multiplicity, it's all about the neighboring protons. It's not about the protons giving rise to that peak. It's protons that neighbor that one. All right? So multiplicity is a measure of protons on adjacent, and again adjacent can also say neighboring carbons. All right? So the protons you're looking at, how many protons are on neighboring carbons? Okay? So if we look at that in our structure, right? So if we look at B, which again is the furthest to the left. If we look at B, go to the left, it's an oxygen. That's not a carbon with neighboring H's. Go to the right, we have 3 neighbors. Right? So B, the neighbor is C, and there are 3 neighboring H's. Right? If we look at A, there are no neighboring H's, right? We go to the carbon next to it, there are no H's on that carbon. So 0 neighboring H's. And then if we look at C, it's attached to one other carbon and it has 2 neighboring H's. Right? So its neighbor is B with 2 neighboring H's. All right, now what do we do with that? What we do with that is use the n+1 rule. All right? So that's the key for multiplicity, the n+1 rule. All right? And what that says is n equals the number of H's on neighboring carbons. And this will tell you the number of lines that your peak is split into. All right? So multiplicity equals n+1, right? And this tells you the number of lines the peak is split into. Okay? So what we'll do is substitute in down here n equals 3, right? So the multiplicity is 3 plus 1, which equals 4. And when we're split into 4 peaks, that peak is called a quartet. Here n equals 0, so 0 plus 1 equals 1. That peak is a singlet. Here n equals 2, 2 plus 1 equals 3. This peak is a triplet. Right, so what will this spectrum look like when you run it? When you run it on the NMR, you'll see a quartet, a singlet, and then a triplet. Right, and this will correspond to B, A, and C. All right. So now what I want to do is look at one other problem. Again, I hope that this and the butylamine problem that we talked about a couple days ago will really help you as you prepare for your homework. So the problem I left you with a couple days ago was from the IR handout, IR problems. It was trying to figure out what type of butylamine isomer we had. And we said that we had 4 different isomers that we had to consider. And we said that we can't tell the difference between these in IR. We need to use NMR to tell the difference. And so I want to focus on the proton NMR for these compounds. Right, so first let's fill in all of the H's. And now let's predict how many peaks we'll see. Don't forget that all the protons are visible, protons on nitrogen, oxygen, sulfur, any of them. Right? So if we focus on these compounds, right, we'll have A, B, C, D, and E. So we'll have 5 peaks from that one. Here we have 2 methyl groups that are the same, A, B, C, and D, 4 peaks. A, B, C, D, and E, we have 5 peaks for that one. Here, we only have 2 peaks. Okay? So we can tell pretty quickly, just from the number of peaks, only 2 of them are going to be the same. We can tell the difference between the other 2 just from the number of peaks. Right, now we can do peak position. And again, we're going to go left to right. The protons on the nitrogen will probably be the ones the furthest to the left, the ones that have the lowest electron density, so we'll always start with those. Right? And then again, we'll just look at the ones that are closest to the nitrogen, the electronegative element. So E, D, C, B, and A. Over here, D, C, B, and A. For this one, E, C, and then you'll note that B and D are equal distances from the nitrogen, so we'll probably just say that B and D will be essentially the same. That will be our prediction anyway, and then A, and then finally over here, B and A. Okay? Now we have to get to integration. Right, and we'll predict the integration in the same order that we're doing the number of peaks. Right, so if we look at E, we have 2 protons from E, so it'll be 2, and then D has 2, C has 2, B has 2, and A has 3. So that'll be the integration ratio when we predict that spectrum. Right, now if we go to the next one, D has 2, C has 2, B has just 1, and A has 6. Right, so that will be the integration ratio. Very easy to tell the difference there. Right, now E has 2, C has 1, B has 2, D has 3, and A has 3. And again, you can see these two have 5 peaks, but from the integration ratios, you can easily tell the difference. Right, and then finally, the last one, 2 to 9 integration ratio. Right, and then finally, let's predict what's going to happen for the multiplicity. Right, so let me just redraw these structures again. And then we'll put the multiplicity right on the structures. And again, we're looking at the protons that we're interested in and how many protons on neighboring carbons. And a key point here is that when you have protons on nitrogens or oxygens, those protons do not split protons on carbon. Only protons on other carbons will participate in splitting. And the other thing is that protons on nitrogen and oxygen will always appear as broad singlets. This is due to hydrogen bonding and things that we don't really need to go into. The key point is that they will appear as broad singlets and not split protons that are next to them. So for all of the H's on nitrogen, we can just say they are broad singlets. So Br space S, broad singlet, broad singlet, broad singlet. Okay? Now let's focus on the protons attached to carbon. So if we focus on the CH2 group, let's get the right number of carbons. The CH2 group nearest to nitrogen has 2 neighbors, so that will make this peak a triplet. The next CH2 group has 2 4 neighbors, so that n+1 means it will be split into 5 lines, so that'll be a quintet, 5 lines. The next one has 3 5 neighbors, that'll be split into 6 lines, a sextet. And then the methyl on the end has 2 neighbors, that'll be split into a triplet. Right? So our 5 peaks, we're going to see triplet, sextet, quintet, triplet, and a broad singlet. Right? When we go to the next one, the 2 protons next to the nitrogen have only 1 neighboring proton on a carbon, so they'll be split into a doublet. Again, n+1 equals 2. The 2 methyl groups also have only 1 neighbor, right? So their signal will be a doublet. If we look at the proton at that position, it has 2 plus 6 neighbors. It has 8 neighbors, so that'll be split into 9 lines, a nonette. Now if we look at this compound, the methyl on the right side has 1 neighbor on a proton, so that'll be a doublet. 1 neighbor on a carbon, excuse me, that'll be a doublet. The H in between the methyl and the CH2 has 5 neighbors. That will be a sextet, split into 6 lines. This CH2 has 4 neighbors. That will be a quintet. And then the methyl on the left has two neighbors, N+1, free, that'll be a triplet. Right? And then if we look at the final compound, T-butylamine, all of those methyl groups, those 9 hydrogens, have a carbon with no protons on them, so that'll be a singlet. All right. So hopefully this analysis helps you as you look through the homework. Again, remember when you look at peaks that are split, the splitting pattern tells you not about that peak, but about the protons on neighboring carbons. The integration tells you the number of protons that give rise to that peak. Right? And we'll talk more about this in class on Friday.